All right, I've got it up here. We get started. This is a block with mass m moving to the right with a velocity of 9 meters per second. Let's calculate its momentum. Okay, so part A, got a block, it's moving to the right. Its momentum P is mass times velocity. The mass is 4.5, the velocity is 9. So that is the momentum there, whatever that is. So grab my calculator. I encourage you to do the same. 4.5 times 9. So it's 40.5 kilograms times meters per second. Okay, the kinetic energy. The kinetic energy is 1/2 mv squared. So that's 1/2. The mass is 4.5. Velocity is 9 squared. So let's get that out. 1/2 times 4.5 times 81, 182.25. That's in joules. Okay, now it says calculate the distance in meters traveled by the block after 5 seconds. Is that right?
Yeah.
So see, this is maybe just a like from old physics, or earlier in the class physics. Your rate or your velocity is 9. Your time is 5. So you get 45 meters for that.
Awesome.
Okay, any questions on that? Or we're just gonna move right through these, I guess.
I just kind of want to move through these.
Okay, wow, there's a lot here. So we got 2 is let me see. Let me grab 2. Pasting it in. Okay, 2 kilogram block. It's moving with a velocity of 4.5 meters per second to the left. Okay, so now maybe to the left, they're considering left negative. That's, I'm not really sure on that completely, but the momentum P is mass times velocity, which is 2 times 4.5. So that's 9 kilograms meters per second.
Oh, okay. So we're just multiplying the two
Yep.
for power?
Yep. Now it's left, so it might be 9 minus 9 because it's left. I'm not really sure. You might want to clarify that with the instructor. So now the energy does not depend on the direction of motion. So the kinetic energy is 1/2 mv squared, 1/2 times 2 times 4.5 squared. So that is 20.25 joules. And then the distance traveled by the block after 5 seconds, that's velocity times time.
Two times 4.5. So velocity times time. Do we have time? We have
time,
velocity.
5 seconds.
Oh, 5 seconds? Okay.
4.5 times 5 again. So that's 22.5 meters left.
5 times 5, right?
4.5 times 5, yeah.
Awesome. All right, so 22.5 meters left. All right, on to number 3.
Number 3. Okay, so number 3 is a as elastic collision. All right. All right, so the 4.5 kilogram from problem 1 clouds the 2 kilogram block from problem 2, assuming the collision is elastic, makes the right the positive direction. What is the total momentum of the system in kilogram meters per second? Okay. So in a elastic collision, I need to just double check this. Elastic collision, momentum. Okay, so the total momentum is the momentum p of the first thing plus the momentum p of the second thing. So you're taking your momentum calculations from the first problem and the second problem and just adding them together.
Okay.
So that's, what is it, 4.5 times 9. And then minus 2 times 4.5 because it's moving to the left.
Wait, so why? So 2 times 4.5. Why is that?
Say that again.
So 2 times 4.5. Why is that again?
It tells you that it's moving left. The second block is moving left. The first one is moving right.
Oh, okay. Calculations. 4.5.
So I get 31.5 for that, and that's kilograms meters per second. That's part A.
31.5 meters per second, or kg
Yep.
meters per second.
Kg meters per second.
Now, what's the total kinetic energy of the system?
So you got kinetic energy of the first one plus the kinetic energy of the second one. The energies are just added together. So it's 1/2 the 4.5 times 9 squared plus the 1/2 times 2 times 4.5 squared. You're just adding those numbers that you got for part A, part B. So you've got 20.25 from B and 182.25. So that's 202.5.
These are in joules, right?
Yes.
Awesome. On number 3.
Part C. Okay, if the 2 kilogram block bounces away with velocity 3, what's the final velocity of the 9 kilogram box? So we have m1 v1 plus m2 v2 equals m1 v1 plus m2 v2, and this is the final side and this is the initial side. So the 2 kilogram box is the problem is these numbers are not. Sorry, I gotta look at the get the numbers again from the equation. So we got 4.5 times 9 plus, actually this one's minus 2 times 4.5. The mass of the first box does not change, and here's its velocity final. The mass of the second box does not change, but it's now bounces back with a velocity of 3. So back means it's going to the right. So we're solving this for V final.
Oh, okay. Do we have V final? Like the 4.5 VF? Does that count as a variable?
4.5 is the mass of the box.
Okay.
So we're just solving. V is the only, I switched V1 to V final, but it's the final velocity of that box. So it's the only variable. We actually already did this calculation in part A. Part A is 31.5.
31.5 equals
4.5.
4.5 F plus 6.
That's right.
All right, so subtract 31. Wait, no. Yeah, subtract 6 from 31.5.
Yeah.
And we get that 25.5. So you get like 5.6666.
Yes.
Round it up.
Exactly. Exactly.
All right. All right, let's get to number D. How much kinetic energy in joules does the 2 kilogram block have after the collision?
So the 2 kilogram block after the collision is moving at 3 meters per second.
Yeah.
Let me get to where I'm seeing the question. Okay, so part D. So for the 2 kilogram block, its kinetic energy is 1/2 mv squared. 1/2. The mass never changes, but its velocity is now 3. So that ends up being 9 joules. The part E is the other block, 4.5 kilogram block. Its kinetic energy is 1/2 mv squared. It's 1/2. Its mass is still 4.5, and we calculated its new velocity to be 5.7. So you have to put that into the calculator. That's 73.1 joules. Was momentum conserved? I want to say no, but let me look that up. It's supposed to be conserved in an elastic collision. So there's a definition here that you have to have, which is that in an elastic collision, this is what I can never remember, momentum and kinetic energy are conserved.
Oh, my bad. I was muted. I asked, can you say that one more time about elastic?
An elastic collision. I mean, I'm just grabbing this from the internet because it's not. I mean, it's nothing super. I'll just snip it in here, but it says that in an elastic collision, there's no net loss of kinetic energy, and both momentum and kinetic energy are conserved quantities.
Momentum and kinetic energy are conserved. Okay. So it is a yes in this case, right?
Say that one more time.
So it would be a yes, right?
Yes.
Okay. All right, now we can flip to the back to collisions, which are inelastic.
Okay. What is the total momentum in kilograms of the system? Well, how is this any different? All right, momentum. Oh, I see. So the total momentum mass in kilogram of the system. Okay. Okay, so for part A, the total momentum of the system is the M1 V1 plus M2 V2 equals M1 plus M2 V final.
Oh, okay.
So because it's in an inelastic collision, I guess they stick together. I guess that's what I'm trying. That's what I'm vaguely recalling.
Mm-hmm.
They stick together. So in this case, we can just calculate the total momentum from over here. We have 4.5 times 9 minus 2 times, I can't remember the number, 4.5. So it seems like the total momentum is still the same. It's the 31.5. Okay.
Mm-hmm.
The total kinetic energy of the system. I don't. I mean, to me, this isn't. There's no difference until there's really no difference until, okay, part B. Part B. Sorry, I'm looking at the wrong question. What is the mass in kilograms of the system? So the mass in kilograms of the system is M1 plus M2, which is 4.5 plus 2. It's 6.5 kilograms. For C, what is the final velocity of the system? So that's where we use this equation up here. We have M1 V1 plus M2 V2 equals M1 plus M2 V final. So V final is M1 V1 plus M2 V2 over M1 plus M2. And we have all those quantities. It's 4.5 times 9 minus 2 times 4.5 over the combined mass of the system, which is 4.5 plus 2. So this ends up being 31.5 over 6.5, which is around 5. So 4.85. And that's meters per second. Will the system be moving to the right or the left? So D depends on the sign of this. So since V final is positive, in this case it's 4.85 meters per second, it's moving to the right. So that first block is moving to the right. The second block is moving to the left.
Mm-hmm. All right, so we're going to the right.
Yeah.
Okay.
All right. How much kinetic energy and energy joules does the system have? To me, this is a repeat of part of the previous question. You have 1/2 mv squared plus 1/2 mv squared. What I'm not clear on, and this is probably what I would ask, is do they mean in the final stage or the beginning stage of this system? Are they talking about after the collision or before the collision? Because after the collision has a different velocity, and it's not conserved. So if that's not clear, I mean, I could show you in the calculation here, because the 1/2 m1 plus m2 v final squared is going to be different than these numbers over here.
Oh.
1/2 4.5 times 9 squared plus 1/2 times 2 times 4.5 squared.
Yeah.
And then over here we have 1/2 4.5 plus 2 times 4.85 squared. And these are not going to be the same. So I'm not sure where to tell you to go on that. We could calculate them both if you want.
Yeah.
Momentum is definitely not conserved.
No conserve. All right.
Okay, can we move into question 5?
Yeah, it's been fun.
Okay, so this one actually gives you some equations that might be useful. It says that gives you the impulse equals force times time. It gives you momentum as mass times velocity. We know that, and distance equals velocity times time. So let's see here. These are the questions that generally just put the numbers in that it asks you for. So 0.5 kilogram football is thrown with a velocity of 15 meters per second. Stationary receiver catches the ball and brings it to rest in 0.02 seconds. What is the force newtons exerted on the receiver? Okay, so the impulse is the change in momentum divided by time, I believe.
Okay.
Does that sound reasonable?
Yes.
I want to look that up though. Impulse is the change in momentum impulse physics, impulse formula. Yeah, so the change in momentum is equal to force times the change in time. So the change in momentum is mass times velocity. So that's the 0.5 times 15. The force we don't know, but the change in time is 0.02. So we can calculate the force as 0.5 times 15 over 0.02.
Oh, okay.
Let me get a number for that, I'm sure. 375 newtons.
0.02. Okay.
Right. Pulling up the next question, number 6. A 0.5. A lot of this is just manipulating the equations that we have, which it sounds like it's easy to do, but you really need some experience to be able to do this. It's not as easy as
It seems.
it seems. Yeah. So, like I kind of already know where to go with these, but I wouldn't expect you to do that either. So we have from the previous problems, we have the change in momentum. The change in momentum equals force times delta t. The change in momentum is mass times velocity, because usually it comes to rest. If it doesn't come to rest, there's a minus mv, but in this case, that's just 0.
Mm-hmm.
So the you can essentially put mv equals f delta t. So you have the force. I'm sorry, you have the mass. It's 0.5. The velocity you don't know. You know the force is 3 newtons and the time is 1.5 seconds. So v ends up being 3 times 1.5 divided by 0.5, which equals 9 meters per second.
All right, on the B.
On to B. So now it gives you new information. It says a constant force, that's F, is applied left. That's your change in time. What is the velocity? So they want the velocity again. So same equation. mv equals force delta t. Your v is force delta t over m. The force is 4 newtons. The change in time is 3 seconds. Almost always change in time is time. And then the mass is 0.5. So that's 24 meters per second.
Oh, okay. MV. On the 7.
All right, posting it now.
Next, we got the multiple choice ones.
Okay. A 2.5 kilogram meteorite traveling at 30 meters per second. So they give you the mass, they give you the velocity, and it made a 0.5 meter hole in the ground.
Mm-hmm.
What force in newtons did it take to stop the meteorite? Okay. So we got change in momentum, delta P equals force delta T. We need to find the force. We've got the mass, we got the velocity, force delta T. So what we don't have is the time it takes. struggling a little bit on this one because we don't know the time. That's no good. Um, I'm not sure if we can calculate the time. It made a 0.5 meter hole in the ground. So it took, there's something I'm missing here to be able to do this. Let me check and see what the internet says. I'm sure someone's done this problem before. I'll give you an answer. If you could observe this, you could measure the time. If you assume some other things, you can also measure the time. So, oh, okay. So the this is a different. This is totally different. We did this yesterday. The change in kinetic energy, or the kinetic energy in this case, equals force times distance.
Oh.
So the kinetic energy here, 1/2 mv squared equals force times the distance. We know the distance, 0.5. We don't know the force, so we're going to calculate that. So it's 1/2, 2.5, 30 squared equals the force times 0.5. And the force, when you do the calculations, 2250 newtons.
All right. Let's done with that. Now on to the number one of the multiple choice.
Yes. So, do you need explanation, or just are we just looking for answers, or?
I'm actually fine with explanations because I don't really understand it.
A moderate force will break an egg. However, an egg dropped on the road usually breaks, while one dropped on the grass usually does not break because the egg dropped on the grass. I want to say there's a couple of answers here, but I really don't know. So the egg is, the ground is softer, but really what happens is it has a little
Momentum
bit of
decreases at the end.
well, it takes more time to hit the ground in some regard.
Oh,
It's kind of awkward to even say that, but that's what it's
trying to say.
trying to say here. So I this is one of those where I'm like, I don't really have a good explanation because
Really understand it.
I don't know which way they want you to go. It did end up being the time interval um, for this is greater because it has more time. So the impulse is different. Um, think of like if you this isn't really the correct analogy, but if you were sometimes when people jump off a building, which is a horrible analogy, but they fall into like this parachute thing. Well, they fall into the parachute and it sort of collapses and kind of springs, and that's what happens with the egg. It kind of has this period of time um, that it's not exactly hitting the ground.
Oh, it's not really. Oh, so for the one where it's like hitting the grass before it hits the ground.
Yeah, it's hitting the grass. So it's kind of giving it some cushion. There's more time that it takes to hit the ground.
Oh, I see what you mean.
That's why the time is greater.
Okay. So is it the change in so the time interval is greater, so it would be D for this?
It's D. Yeah.
Okay. Let's just check these. All right. On to number two. So a child falls sideways off of a sled while sledding on frictionless ice. What happens to the velocity of that sled?
So my initial guess is that it increases because you're pushing away from the
Mhm.
sled, but the mass also goes down. So,
Interesting.
these are not. I mean, I'm not sure. Yeah, that's the
It says I checked the internet and it says it remains the same. How does that happen?
It's a mass that must not matter when it comes to velocity.
Oh.
Yeah, I can't give you a good explanation on this. Unfortunately, it's not my. I can help you do the math, but these explanations aren't real clear to me. Why does it remain the same? Because mass probably is not relevant on frictionless ice. Friction is based on mass of the object,
Mm-hmm.
and that's why it probably remains the same on there.
On number 3, which of the following statements properly relates the variables in the equation F force times time equals what's P?
Momentum.
Oh, equals momentum. Okay. So
Force and time. No, a large constant force acting. Force and time are directly proportional. The bigger the force, the longer the time. Oh, D is down here. Okay, that's why I couldn't figure this out. Force and momentum are inversely proportional. The larger the force, the smaller the change in momentum. No, that's not true. Um,
is it directly proportional? C?
yeah, I want to say yes, but no. It's force. This isn't right. It should be force and time are inversely proportional.
That's really odd. So what do you think it would be in this case?
What does it end up being?
Hmm.
So what do you want to do here, Jack? Because I mean, this isn't really in my comfort zone to be able to give you proper explanations. Is there something
Yeah.
else we can do?
I just kind of
Um,
want to get through these. I just want to find the answers to these.
I mean, I can do that, but it's not going to be very helpful for you. But I can scour the internet and find what we need here.
Mm-hmm.
So it says a large constant force acting over a long time interval causes a large change in momentum. So A for that.
All right.
Why didn't I bold that? Okay, two objects stick together and move at the same velocity after colliding. That seems like an inelastic collision. Check here. This is a perfectly elastic collision. I guess that's a straight definition. The law of conservation of momentum states that the total momentum remains constant. Remains total momentum of all objects interacting with one another remains constant relative to the forces between. So I think it's B. It remains the same. So the total momentum remains the same. So it looks like that would be. Sorry, I'm getting back to this. It remains constant.
The B.
Yeah.
All right. On the 6th. If you're skating at 3 miles speed, it's a velocity.
An ice skater skating which 3 meters per second sees its velocity finds the momentum of the skater. Well, we can actually answer this. So this momentum is mass times velocity. Its mass doesn't change. So if the velocity increases, the momentum increases.
So it's just D.
Yeah.
All right.
Two skaters stand facing each other. One skater's mass is 60 kilograms. The other mass is 72 kilograms. The skaters push away from each other without spinning. The 60 kilogram skater travels with a lower momentum. Their total momentum are equal. Okay. So their momentum is their combined mass. I'm gonna say it's equal and opposite, but I gotta check this. This is uh, yeah, equal and opposite. So the idea is their initial momentum is zero because they're not moving. When they move
Mm-hmm.
apart, you have m1 v1 equals minus m1 v or m2 v2. That's why it has to be equal and opposite.
Makes sense.
So the 72 kilogram person is traveling slower than the 60 kilogram.
Yeah, because the mass is
Yeah.
less, right?
Yes. Golf ball traveling 3 meters per second right collides head on with a stationary bowling ball in a friction free environment. The collision is almost perfectly elastic. The speed of the golf ball immediately after the collision is, uh, well, I would say it's got to be less than the three because it but let me check that. The problem is like what you think is true may not actually be true.
Yeah, like you can't think necessarily logically.
Yeah, I can't say, well, I don't know. In this case, it is less than 3 meters per second.
Would you say much less for D?
No, that's a good point. Eh, this is one of those things I we don't really know what much less means.
Mm-hmm. To me, I feel like it would be like 1 meter per second or something. I don't know. Just like going, just kind of plummeting.
Yeah, and is that much less? I don't know.
What does that mean by perfectly elastic again?
We got a definition up somewhere. It means that momentum um, and kinetic energy are conserved.
So wouldn't it be slightly less?
That's why, yeah, that's why I went with slightly less on this.
Okay, so I will go with A here. All right, let's go for 9.
So when a tightrope walkers walk the long flexible rod, what it does is it centers their mass, but it also lowers it on the object, so that they don't actually they're not as high up off the ground.
Does it increase their total weight this time, or what is it for number 9?
It lowers their mass, increases their total weight. It's usually not very much,
Oh yeah.
but that's a good answer.
Move faster along the rope is not the goal. Lower their center of mass. Aren't they technically lowering their center of mass when they're doing that?
Yes.
So that would be D, right?
Yeah.
Okay. Okay. Let's go on the number for the last this is 4, last 4. A rubber ball with a speed of 5 meters per second collides head on elastically with an identical ball at rest. What is the speed of the initially stopped ball after the collision?
So it's going to be the same speed. That's because it's elastically. So like everything goes to the other one.
Oh,
It just bounces away. I mean, this is like the billiard ball example. You hit one ball into the other, and it goes basically away at the same speed.
so D.
Yes.
All right, on to number 11.
So we know the momentum before is 3 times 12 plus 6 times 2.
Yeah.
Actually, it's 0 because one's moving left, one's moving right. So my guess is that the total momentum both before and after collision is 0 because one's going to move left and one's going to move right. But I don't know. This is where you really need a physics expert to answer these, because they study this stuff in a way where they try to understand these things. I don't. Object. The total momentum both before and after the collision is 0. And I assume that's because one moves left, one moves right afterwards, so you get the same thing. Because before the collision, you got one going left and one going right, so that's why one's positive, one's negative.
Wait, so which one would it be?
C.
C?
I'm highlighting them as we go. I don't know if you're looking at that document.
Oh, sorry, I'm not looking at that.
Okay.
That's what was happening.
I've been highlighting them, yeah, pretty consistently here to help.
All right. On to number 12.
All right, the red ball rebounds. Okay, so 2 balls are dropped from the same height. The red ball rebounds to a higher position. Which ball is subject to the greater magnitude of impulse during its collision?
What's magnitude of impulse?
Momentum times time.
Okay.
So the one that stays with the ground longer will not bounce as high, and that one will have a higher impulse. So the red ball has a lower impulse, and the blue ball is a greater one because it's not going as high.
So we'll go for C.
Yeah.
Last one.
So the greater momentum change is always the one that comes to rest, because it's changing momentum. MV minus MV. The first MV is always the same. The second MV is going to 0.
Mm-hmm.
So I want to say it's the putty, but this is one of those things where well, does the final velocity move away? So it's negative. So then you end up getting a greater change of momentum that way. Let's find out. So it says the ball. So that must be because the momentum, you end up getting your MV minus MV. It's really MV minus MV, which equals them both being positive, rather than MV minus 0.
That's interesting. I think that wraps up everything I wanted to cover today. Thank you, Matthew.
Jack. Thanks for scheduling. I'll see you next time.
Have a nice day. Appreciate it.